Before the break, I made a few promises about deep learning, so now I'm going to try to convince you that they are true. I'm going to review some important concepts here, backpropagation and how deep neural networks can be trained. Those of you who had machine learning last semester already got a first look at this, but since there is no it's not mandatory to do machine learning before this course. We will go through briefly this important algorithm for training neural networks. Then we're going to look at stochastic gradient descent, how we can actually in practice improve the performance of the network by experience, by showing it examples. And then I'm going to give you a brief overview of deep model architectures and the relation with unstructured data. So remember that the motivation for using deep learning in this course is mostly so that we can process unstructured data. And I'm also going to give you some examples of how deep learning models can be used with unstructured data, so actual examples of applications, and try to explain why the recent success of deep learning. So remember that we were looking at this historical overview of artificial intelligence and machine learning, and these things date back to the late 1950s. So why only now did these techniques really flower into these successful applications. So let's start with backpropagation. This is the algorithm we use for training neural networks. A neuron, as we saw previously, is this combination of a linear or a weighted sum of the inputs, so a linear combination of the inputs that gives us this net value here, and then followed by a nonlinear activation function. This is very important because remember, we need to have some nonlinearity somewhere in order to be able to transform our data and to do something more powerful with it. If we just do this, just one nonlinear activation here is not enough, and this works as a linear classifier. But if we can chain together these different modules, then we can get increasingly complex representations of our data using these nonlinear transformations, and this is how the magic happens, so to speak. So to propagate the error through all the way until we find the parameters. These weights are the parameters we have to adjust, but the error we need to measure here on the output when we compare the output of our network to the target that we want. In order to be able to compute how to adjust each step, each parameter along the way, we need to be able to compute the gradient, the derivative of all these functions along our network. So we cannot use this original function that Rosenblatt proposed. This was the original function for the perceptron, which it was enough for a single neuron because that update rule that Rosenblatt proposed worked. But we cannot then chain together different neurons because this step function, we cannot compute the derivative, and so we cannot propagate the error backwards, as we're going to see soon. So we need to use functions for which we can compute the derivative. For example, the sigmoid activation function was a very classical example of this. It's similar to the original threshold function, but it's smoother, and so we can compute the derivative for that. Okay, so the idea now is to propagate the error or the effect on the error of each parameter all along the network. So let's say we are training one single neuron and we are trying to minimize the quadratic error, so the square of the difference between the output of the network, for example, J. So this Sj is what the network is, or the neuron in this case. The network is only one neuron in this example. So in this case, the neuron is outputting this value S when we give it example J. But we wanted the value to be this T, this target. So we measure the difference, we square the difference, and now we're going to try to minimize the sum of all these errors for all our data set. And the idea now is that for the examples, we are going to figure out how to adjust the weights or the parameters of our neuron. So remember that we are measuring the error here at the output, but the parameters that we want to adjust are over here. So now we need to figure out how to adjust the parameters in order to minimize the error that we have here. And we can do this by giving a small step in the direction where the derivative of the error with respect to some parameter, here some weight, is negative. So we're going to go down the derivative of the error with respect to the weight. However, to do this, we're going to chain together these different functions. So the activation, the sum here, the weighted sum, and so forth, and the error function too. And this is what we have here. Our error function at the end is this quadratic difference, the square of the difference between the target and the output for the example. So the derivative is this. By the way, this 1/2 here makes no difference because we're trying to minimize, we're trying to find the weights that minimize the function. But if we divide the function by a constant, the minimum will be exactly at the same point. And this is convenient because of the square there. When we do the derivative, we get a much cleaner function because it cancels out the 1/2. So the 1/2 there is just for convenience in the expression. Now we have the activation function, which is this sigmoid over here. So we have the derivative of the error. The derivative of the activation function is this one. And now we go all the way back to the weighted sum here, where the derivative with respect to one weight is simply the input value that is multiplying by the weight. So this is this part here, which is the input value corresponding to that weight. So now we have an expression that allows us to adjust the weights of the neuron by sliding down the derivative or the gradient of the error function for each example that we present. So intuitively, this would be our expression. This gives us the direction where the surface of the error function is going downwards. So this is the derivative of the error for that particular example. This is a small value so that we don't give steps that are too large and then cause numerical problems in the convergence here. So this would be the learning rate, typically around 0.1 or lower. So we are going to use this in order to find out how to update, how to adjust the weight. And the intuition for this is basically that we have a target value and the output of the neuron. There is an error function between these two that we're going to use here. And also we have the derivative of this sigmoid function, the activation function, and also the derivative of this weighted sum, which basically with respect to W would be the input value there. So this is using the chain rule. We're going to multiply all these derivatives and compute the update for our neuron. Now, how we can do this in practice, there are several different ways, but we can imagine that we have this average, the surface that tells us the average quadratic error for all our data set. And so this could have a specific direction when we are here, for example, but when we present each example, we can have a slightly different direction because the examples are all different. This would be the average surface, but each example would be slightly different. So this is the idea of stochastic gradient descent. If we give the examples in a random order, then all these small steps will be in slightly different directions in random order. And this is why this is called stochastic. This is a typo here, should be a C. Stochastic gradient descent, because we are going down the gradient, but using some randomness there because of the order of the example. In this case, online learning, we are taking one step for each example. So we receive an example into the network. We compute the error between the target value and the output. We compute how to update each weight, and then we change all the weights. And then we repeat that for another example and another example, and we go gradually sliding down the error surface until we find the best position, the best combination of parameters. Another way of doing this is using batches. So instead of trying to estimate the shape of this error function that is average for all the possible examples, using only one example, we can use a batch of examples. We can use the whole set of examples, but this generally doesn't work too well. But we can use a small batch. We take a sample of examples and we use those. We compute all the directions, all the derivatives for those. We add them all up and then give one single step on the optimization. So this is generally how things work in practice. We have these batches. We group together, say, 64 examples at a time, and then we compute all these updates for all the examples, but we do not change the network between different examples. Only at the end of the batch, we add up all the different updates, and then we change the network once. This has some advantages in giving us better estimates for the direction, while not losing this randomness that allows us to find better ways along the better paths along the surface, and also can be good for optimization because we don't have to change the network so many times. We can parallelize these different operations, for example, using tensors. We're going to see that in TensorFlow, and so we can greatly speed up computation by using batches. Okay, so if we do this with a single neuron, we get something like this. This is the error we are getting on average for each epoch. So each epoch is a pass through all the examples that we have. At each epoch, we're going to present the examples in some random order, and we're going to start reducing the overall error that the classifier is committing until we reach some convergence. It doesn't appear to be able to improve beyond that. It reached the end of its capabilities in this particular example. Okay, so the big advantage of backpropagation over what, for example, Rosenblatt proposed, that update rule, is that we can extend this, we can generalize this for multiple layers of neurons, so deeper networks. For example, suppose that we have this network, we have the input values here, we have one layer of neurons, but then these do not give us directly the output. They will be fed into another layer, and we get the output from this one. So now we have, instead of having the inputs feeding into a neuron that gives us the output, which was the example before, we now have the inputs feeding into neurons that feed into other neurons, and so on, and eventually we get the output. So to do this, in this example, we have just a fully connected feed-forward network. This is called a multi-layer perceptron, so following the same idea of the original perceptron, but now adapting for these different functions and multi-layers and so on. But we have different layers, and each layer is fully connected to the next layer. We call all these layers before the output layer the input, the hidden layers. The input layer is simply the vector of inputs for each example. And then at the end of the multi-layer perceptron, we have the output layer. And what we can do here for training the multi-layer perceptron with backpropagation is, for the output neurons, we use exactly the same expressions that we used for a single neuron, but we, instead of considering the input values, we are considering as inputs the output of the previous layer. But other than that, it's the same thing. To compute the derivative with respect to this, to the weights here for this neuron in the last layer. So basically, we are looking at neuron N of layer K. Layer K in this case is the last layer. In this simple example, we only have one neuron on the last layer, but in theory, we could have any number of neurons in the last layer. And so to update the weight of one weight of that neuron, we can consider the same chain rule. We're going to look at the error function, the derivative of the error function with respect to the output of this neuron, and then the derivative of the output with respect of that weighted sum of all the inputs in into the neuron, which would be these inputs here. They are coming from the previous neurons, and so on, and then the derivative with respect to the weight that we want to update. Now, for this, we have this part here that we can compute as a function of the neuron. And then what we have instead of what we had here, which was the input value into the network, which in this case was only one neuron, so the input was fed directly into the neuron. In the case of the output neuron, the input value that we're going to consider is the output of a neuron in the previous layer. So if we are considering this particular weight here, we have to consider as the input value the output of this neuron. This is what is being fed into the output neuron through this weight. So basically we have this expression that depends only on the activation of the neuron, the error, and so on, and then we are multiplying this by the output of the previous neuron that is going through the weight that we want to update. So we can do this, we can compute this and compute how to update this weight. Now the things get a bit more complicated when we are looking at updating the weights of neurons inside the network, because a neuron here can be contributing to several neurons in front. And so we need to keep propagating the error through all of those different paths until we reach the parameter that we want to update. But basically the idea is the same. We are chaining together the derivatives, so we are multiplying all of these derivatives. And so we start with, at the end, the derivative of the error with respect to the weight, the output of the neuron in the layer in front, and then keep chaining backwards those derivatives, and then we go through our own neuron, the one that we're trying to adjust, by going through also its activation function, its weighted sum, all the way until we find the parameter that we are trying to adjust. So the thing is that we're going to have to sum this for all the neurons in front, but we can do this with backpropagation too. So this is just a generalization for an arbitrary number of neurons in an arbitrary architecture of the network. Okay, so in the intuitive explanation here is that if we're trying to adjust this weight, we need to trace back the error between the output of this neuron and the target, the activation function, the sum, and this particular weight until we reach this neuron, and the same thing for for all the neurons this one will contribute to. So this is the sum that we have here for all the neurons in front. And then we keep tracing the error through the activation of this neuron and the weighted sum here until we reach how we compute how much we have to change the weight, this particular weight of this particular neuron. So the algorithm is basically to input the values into the network. So we have an example here that we present to the network, and then we're going to propagate forward the activation of the network. Each neuron will receive its inputs, compute the activation function, and then feed into the next layer, and so on. So this would be the first step to light up all the layers of the network by computing all the activations. And now for each neuron, we can start computing these delta factors that will be the same for all the weights in that neuron, which correspond for the output neurons to this expression, assuming we have a sigmoid activation and a quadratic error function, so the same functions that we have. We can compute these are the products of those derivatives, and then we can backpropagate this and compute all of these for all the neurons going backwards using the weights that are connecting the neurons. So basically we compute this for the output neurons, and then we go back and compute this for the hidden neurons, and go back all the way until we reach the beginning of the network. And that's why this is called backpropagation. We are propagating the error backwards through all the parameters in the network. And now once we have this computed, we can just update all the weights of our network by using these deltas that we computed for each neuron, and multiplying by the input that is going through the corresponding weight. So if we are in the beginning of the network, then going through a weight is the actual input value of some feature of the example. If we are in the middle of the network, then the input that is being fed into one neuron through its weights is the output of the neurons in the previous network. But this, we computed this in the first step, so we have all these activation values we can compute for the whole network. So this is the basic algorithm that we're going to use to train any network. And as you can see, it doesn't matter how many neurons you have, how you connect them, and so on. As long as you can figure out where they are connected and activate them, you can use the backpropagation algorithm to adjust the parameters and train the model. So the combination of this with the power of artificial neural networks to transform the data gives us a very versatile type of model that we can adjust at will by changing the architecture depending on the problem that we're trying to solve. So the general outline for backpropagation would be to present an example to the network, propagate the input forward through all the layers, compute all the activations in the network, and then starting at the end, compute all these derivatives, the derivative of the loss function, and then going backwards, propagating through all the activations and all the neurons until we compute all the weights. And then we can do this for a batch of examples, add all these updates, and then change the weights of the network after we finish computing the batch. So this can be used for different activation functions, different loss functions, different architectures, ways of connecting the neurons, and so on. We're going to see lots of examples of this. It's always the same basic idea, but as long as we can compute all these derivatives, and that is really the requirement here, that we can compute the derivatives, we can apply this algorithm to any kind of architecture and train the network by adjusting the weights depending on the examples. So if we stack these layers, we are now stacking nonlinear transformations, and we can improve the power of the network to solve problems. So we saw that if we have just one single neuron, then we are limited to the kind of separation that we can do to our data, because now it's only a linear classifier. But if we add a hidden layer with a nonlinear transformation, so all of these neurons have that sigmoid output, then these neurons will respond differently depending on their weights. And this is what the output neuron is seeing. So the output neuron is not seeing directly the data, is seeing the output of the hidden layer. And this is what things look like from the perspective of the output neuron, where depending on the response of neuron 1 or neuron 2, I'm representing the two neuron outputs here as two directions, we are going to, as the response change, this one is going to see the data transformed in different ways. So now if we can imagine that we can draw a straight line here to separate red from blue, it becomes increasingly easier to do so. So this one can only do a straight line, but it's making this straight line on the transformed data set, where it's a lot easier to separate the classes. And if we transform this straight line backwards to what it would mean at the original representation of the data, it's actually this bent line here that starts to improve the classification. So this is really the power of stacking these nonlinear transformations. We do not have to specify the nonlinear transformation. We don't have to choose the kernel or things like that, like we do in support vector machine. The transformation is learned by the network itself using backpropagation. And we can stack all the transformations that we want. For example, we can add a hidden layer here. So this one is looking at this difference between the last one is looking at this kind of representation. This is just a representation of the output, because this one goes from 0 to 1 and is trying to separate the two classes. So this output neuron is seeing this representation here, which is given by these two neurons in this hidden layer. However, these two neurons are also working on this representation that is being learned by this hidden layer. And only this one is looking at the original data there. So we can stack this and increase the capacity for dealing with more complex problems. For example, here we have the red class in the center and the blue class all around. And the important thing here is not only the power of these nonlinear transformations. We have that in other examples in machine learning, like support vector machine and other classifiers, but neural networks actually learn how to do these transformations depending on the data that we feed them. So it becomes a lot simpler just to feed in the data into the network and let it figure out how to best transform the data in order to solve the problem. So with this we can build very powerful models just by stacking layers of neurons, or in other ways. We're going to look at different architectures, but this is the general idea of how to take advantage of this capacity. Okay, so now how do these compare with the shallow models that we have? So with the linear models, we are limited to just linear classification, and the idea is that we choose a set of features, we extract those from our data, from our raw data, and we present these features to the linear classifier, and it will work with those. This works well if we can really pinpoint what kind of features that we want, and if the problem can be solved with a linear classifier. If we have some more complex problem, we can still choose correctly our features, choose the nonlinear transformation that is more adequate for our problem. For example, the kind of kernel that we use, the kind of way we extract features from the data or something like that. But we need to choose these correctly. We need to choose an appropriate transformation and the right features in order for the thing to work at the end. Otherwise, remember the no free lunch theorem. We cannot just assume that any model will do. Some models work well in some cases, others work well in others, and we cannot really just use one for everything. So we need to figure out what the transformation is, what the actual model is we're going to do, what are the features, and so forth. Now, with deep classifiers, with deep models, this works differently, because of this stacking of nonlinear transformations, nonlinear responses along the networks, added to the ability to learn the adequate parameters, so to learn what kind of transformations we are useful to solve our problem, we can just stack these layers and do a set of nonlinear transformations until the problem gets solved. And we can just play with these architectures, add more layers, take some layers, and so on, until we optimize the process. But we don't need to invest so much in finding the appropriate features or finding the appropriate transformation, because that's what the network can do by itself. And when we look at this, so this is an example, a real example from convolution networks. I'm not going to detail what convolution networks are here, because we're going to cover these in a few weeks. But the idea is that when we look at the first layers, these are the maps that most strongly activate some neurons, or in this case some kernels for the convolution. And we can see that on the first layer, the network is representing the images that we presented with as sets of things like diagonals, horizontal lines, contrasts, and things like that. So it's breaking down the image into some elementary features about the image. And then when we move up the network, it's starting to find things like circles and so on that are combinations of features extracted on the previous layer. And it moves on until it finds more complex things. So as we move further on along the network, the neurons there are responding to more complex patterns in the images. And this is very useful for this kind of unstructured data. I'm going to talk a bit more on this, but it's very useful because if you have a set of images, it's not trivial to figure out what kind of features we want to extract, how we want to convert these images into a set of informative numbers. But the network learns how to do that. It learns to train the neurons to identify specific patterns at some higher level of abstraction based on some lower level representations and so on. And by stacking all these representations, it eventually finds the right patterns to solve the classification problem that we have. So let's see the relation between this and unstructured data. If you took the course, the machine learning course last semester, we used structured data. This is basically all data sets that you can just put on a table and where you have well-defined semantics and meaning for each particular example. The exception to this was the final assignment where we looked at images of cells, but in that case we did first an extraction, a feature extraction, and then we had a table with the different features that were extracted from the cells. So basically this is structured data. You have a table and each column on the table means the same thing. This can be different things like blood pressure, glucose levels, the average brightness of all the pixels, the largest component in PCA or something like that. But you know what this column means for your data. And we have all the examples with the same set of attributes. So they have all these different columns filled out for our examples. But although this is easier to use for machine learning, we have all these known attributes, all the different columns. We have the same size input for every example. We know what each attribute means, but this usually requires some human intervention. If you have raw data, you need to select the right columns, you need to pre-process the data, probably compute some derivative values that are more useful as features and so on. So this kind of data generally requires a lot of preparation by humans, either when you're going to apply the machine learning methods or before that when the data was actually generated and each thing was properly labeled and placed in the right column and so on. We can have lots of cases of semi-structured data where it's not exactly a table, but there is some structure that you can use. For example, XML, JSON, things like that, metadata for emails where you have the sender, the timestamp, and so forth. Usually, it also requires a lot of work to keep the data correctly stored and also to organize the data. But generally, we deal with semi-structured data by manually converting this into structured data, into a table. So if you are processing emails, you can extract the metadata from all the emails and put it on a table, and then you have all those values there. But a lot of information is stored in unstructured data. So we have this estimate by Merrill Lynch in 1998 that was 80 or 90% of useful data was in unstructured data. My guess is that this is just a number they picked out at random because there's really no way of computing this, but it's obvious that a lot of information is not stored in neat tables with fixed columns where we know what things mean. We have documents, text documents, we have video, photographs, sound recordings, web pages, the interconnections between web pages, everything in social media. There's a huge amount of data that we cannot just put into a table because it has no structure like that. So basically, this is a big motivation, especially when you're dealing with big data. how to use this unstructured data in order to work with it, train some models, do some predictions, and so on. And this is difficult to do with classical machine learning, where the human needs to extract the features. So if you have a set of text documents, for example, if you want to apply support vector machine or something like that, or random forests or other classical algorithms for doing classification or some kind of problem, you need to think of which features you're going to use. So maybe you're going to do statistics on the kinds of words that appear, the size of the document, the formats, or things like that. And you need to build a table with all these features in order to feed into your machine learning algorithm. So the advantage here is that compared to this classic approach where you need to explicitly convert everything to structured data, and this can require techniques that may take years to perfect. So if you are dealing, for example, with medical documents, if you, after a few years, you already know what kind of words are important, what kind of fields have been filled in some particular way, and things like that. So you can write some scripts that can convert those documents into a table and give you some meaningful features. But this can take a lot of work and a deep understanding of the field in order to be able to do this. If you go for deep learning, then this helps solve a lot of these problems, because instead of having to do this custom feature extraction where the human thinks about which features to use and then chooses the nonlinear transformation and so on to apply with the methods, we can just feed the raw data into a deep neural network, and the neural network will figure out how to transform this data into something that can be used to solve the problem. One particular notable example of this is image classification. Images are unstructured data. We cannot tell which pixel is what in an image or in the whole set of images, but we can train a deep neural network to find the appropriate patterns and the correct representation of the images in order to perform some classification task or something like that. We can even use this ability to extract features from data by finding the best representation. So I'm going to give just a very simple example. This is actually a classical example from Mitchell from the 90s, which is the AutoEncoder. We're going to use this in a bit more sophisticated in the tutorial classes. But just to illustrate, suppose that we have a data set that is composed of vectors of 8 numbers. So these are 8 squares here, but each vector only has one number at 1 and the rest is 0. So this would be the first example, 1 followed by zeros. This is the second example, 0, 1, and then zeros, and so on, and we have all the 8 examples here. Now we have a neural network that inputs these 8 examples, has 3 neurons at the hidden layer, and then has to output on 8 neurons also 8 values. And we want to train the network in order to make this output here equal to the input. So when the network receives this set of 8 values, it outputs this set of 8 values. When it receives this set, it outputs this set, and so on. So this is called an autoencoder because it's just outputting the same as the input. When we start the network, we initialize the weights at random, and we get mostly garbage. So if we input this value, this vector here, 1 followed by zeros, we get this thing here, and this is the activation of the 3 neurons inside the network in the hidden layer. So basically in the beginning, this is just garbage because we have all the weights set at random. But after lots of iterations of using backpropagation, we are adjusting all the weights in the network in order to be able to reconstruct as faithfully as possible each input correctly into the output. So when we give this input, this is the output. For this one, it's this one, and so on. And the network now can give us back exactly what we give it as long as we follow this same pattern, because it was trained for this pattern. If we use some different kind of examples, for example, with 2 ones, probably the network will not be able to answer properly there. But what is interesting here, of course, getting the same result as we input is not particularly interesting, but what is interesting is what's happening in the hidden layer. Note that for this particular input, 1 followed by zeros, we have 1, 0, 1 in the hidden layer. For this input, we have 0, 0, 1, and then we have 0, 1, 0, and so on. And we have all the 8 combinations of 3 bits in the hidden layers. So basically, this simple network learned how to encode the 8 different inputs that we give it into combinations of 3 zeros and ones. So it created a code, a representation of the data based on the pattern that we have on our data. So this can be used, this kind of approach can be used for manifold learning, for trying to learn what is the shape of the data, but represented it in much lower dimensional space. For example, this is the UCI banknote dataset. We used this last semester in machine learning, and basically it's a set of fake and real banknotes. For each banknote, there are 4 attributes that describe the banknote, the entropy on the image and things like that. So we have a 4-dimensional dataset. We can reduce this into 2 dimensions and project it by using, for example, PCA, principal component analysis. We try to preserve as much of the variance as possible, and then we project this into the 2 main components. But as you can see, there's a lot of overlap here between real and fake banknotes because of the way the data is distributed, and PCA cannot really disentangle them. One alternative is to use an autoencoder. So you have an input of 4 values. These are the original values of the banknotes. And this particular autoencoder I created using 6 neurons, then 4, 2, 4, 6, and then 4 neurons as output. So note that this is symmetrical. We have the same thing going out as we have going in. This is a typical architecture for the autoencoder. But the thing that we are interested in is these 2 neurons here. Because we start with an input of 4, we end with an output of 4, and require that the values that are output here are exactly the same as the ones that were input. So the autoencoder needs to be able to reconstruct all these different examples. But we then go pick out the values in these 2 inner neurons. And this is what the data looks like after encoding only through this part of the network, after we train the network with all the examples. So you can see we can now separate the two classes a lot better, because the neural network learned to represent this data in a more compact manner, but that still preserves these relations between the different vectors as much as possible, since we were requiring it to be able to reconstruct the original values from that representation. So this is an example of unsupervised learning with neural networks, and is very useful for unstructured data. In this case, we use it for structured data, but we can use it for unstructured data, for images and things like that, because we can find a good representation for any kind of data that we have. So deep models can learn to extract the best features, and so they are very useful to avoid having us to do this manually, extracting the right features. Can learn to encode data even without labels, even unsupervised, and this is done automatically by the model. So as we apply backpropagation, the different layers will learn different representations of the data. So why is deep learning so much in fashion now? The thing is that deep learning is not very good if you have small data sets, because this only works if we have a large network that stacks different transformations. And if we have a very small data set, then we end up overfitting. We have a model that is too powerful for the data, and so it will not perform well. So if we, in the previous years, before deep learning started to really show its abilities, most problems had smaller data sets, and in that case classical machine learning with simpler models can actually perform better than deep learning, because deep learning suffers from overfitting. But as we increase the size of the data, as we increase the complexity of the problems, the classical approach starts to not have as good a return, because extracting the correct features becomes increasingly complex, increasingly demanding of human intervention. The models are also limited, because we have a lot more trouble choosing the right models for the data and so forth. Whereas with deep learning, we just stack larger and larger networks, and as long as we have hardware to solve everything, basically we can solve problems much easier if we have enough data. So this was one of the reasons why deep learning took so long to really take off and to show how it was better for these kinds of problems. So for example, in 2006 there was this Caltech 101 dataset that had these 101 groups of images, about 500 images for each category. So they varied from, 50 images for each category. They varied between 40 and 800, but on average it was around 50. And classical computer vision models managed to classify or identify images in this data set with about 26% of error when picking the categories for the images. And this was not very good for deep learning, because there were few examples, and not very good for training these deep networks. Also in 2006 we did not have as good hardware and as good computation techniques, algorithms, for example, activation functions and optimizers and so on, to actually work with deep learning here. But there were lots of improvements in algorithms. For example, rectified linear units in 2011. We're going to talk about that next week. Or in ways of training deep feed-forward neural networks. And also improvements in hardware. So these general purpose GPUs were very good, because the ability to use graphical processing units for general purpose computation really gave a large boost to artificial neural networks, because GPUs are used for parallelizing simple matrix operations, and basically neural networks are simple matrix operations that we can parallelize by doing all those multiplications and sums really quickly. Of course, more recently we have actually these tensor processing units, or the Nirvana from Intel. So Google developed their own circuits, and Intel too, and these are very specialized and very powerful for neural networks. So they are hardware built specifically for deep learning. And with larger data sets, for example, from 2012 onwards, we have this benchmark data set, ImageNet, that has 1,000 categories, so a lot more than the other one, the Caltech one, and it has 1.2 million images. So on average, it's over 1,000 images for each category. And now here, large convolution networks became dominant. So in 2012, we started this competition. They were basically competing with the classical computer vision algorithms and machine learning algorithms. But this AlexNet, this deep convolutional neural network, was the winner, with only 50% error in the top 5. So this top 5 error is the network gives the top 5 categories for an example, and in only 50% of cases the correct one was not in these top 5. Remember that these are 1,000 categories, so it's not that easy to get right, even with these 5 tries. But in this case, convolutional neural networks were always the winners of this competition. So 2012, 13, 14, the error kept going down. Eventually it starts reaching the fraction, the error rate of humans. So the labels themselves are not entirely correct because humans sometimes make mistakes, and we start reaching the limit of what we can do with the data because humans are not infallible. So just to give you a few examples, this was the first, this AlexNet, the first one that started being used in this competition. It used two NVIDIA graphics cards, these GTX 580, because they could not fit the whole model and the data into a single card because of memory limitations. So basically it was decomposed into two halves. But they used these two cards. This is the network architecture, the input image. Then we have lots of layers of convolution, and then here we have these dense layers. So this is a multi-layer perceptron with a few thousand neurons in these layers, and then 1,000 on the output to output the different classes. So each neuron is responsible for saying whether or not the image belongs to that class. So we have a huge number, millions of parameters here to optimize, but using the GPUs and a large data set, it was possible to fit this model. Then things started getting even more complicated. For example, GoogleNet is a much larger architecture. Of course, by 2015, there were better hardware available, and the error rates kept on reducing. And so for image problems nowadays, we have this, for example, VGG19 has a 75% accuracy on the top class. So for 1,000 classes in this data set, it can get right exactly the correct class 75% of the time, and 92% of the time it gets the correct class within the top five predictions. Then we have these even improvements, so continuous improvements. For example, the latest version of ResNet, at least that I know of, already goes to 97.7 on the top 5 accuracy. We have specific nets. For example, eNet is a very efficient network for real-time semantic segmentation. Semantic segmentation is not just identifying the class of the image, but assigning each pixel to a different type of object. For example, one part is a person, the other part is a car, things like that. And it can really do this in real time. You can present a video, and the network is classifying each frame and working with that. Then you have specialized networks. For example, ShuffleNet does image classification on mobile devices. You can have these kinds of networks on your mobile phone, and they don't require lots of computing power to use. Of course, they require lots of computing power to train, but once they are trained, you can use them in these devices. So there are lots of different architectures and networks for this kind of problem, and there are also different problems. I'm just going to give an example, an interesting example here, which is a network for generating visual explanations. This is actually a set of two different types of networks, but they were trained using these 12,000 images of birds of different species. And there was in this training set sentences explaining what each bird is like. And the idea is that the network can identify the bird from the image and then generate a sentence explaining why why it seems that this bird belongs to that species. So this is basically one convolution network that does the classification for the images, and then one recurrent network, these long short-term memory networks, for generating sentences, for generating strings of words. Actually, it's two networks, but we don't need to go into those details. And the idea of these networks is that you have these modules that have different types of activation functions and connections, but basically they receive an input from the previous state of the same set of neurons, do these operations by the weights, and then the output goes back into the same block. So we are looking at this as unrolled. We can imagine this as a sequence of blocks, but it's actually always the same block, the same set of weights, and is feeding these parameters into itself. So it's kind of changing over time as the output is fed in as new input, and we can use this to reproduce sequences of data, sequences of values, of events, of words, things like that. So if you use a large number of these in parallel, you can encode different words and then use them to output the right words and to learn the patterns of the sequences of words. So basically, they have this neural network for classification, the neural networks that are generating the words. There is, in the loss function, two terms. One that gives a measure of how relevant the words are. So it basically looks at the probability of having this word if these other words occurred before, because the sentences need to make sense and the words cannot appear at random. But also they want the sentences, the descriptions, to be discriminate. So they need to discriminate between different birds, and we want to have some words that appear more often in some classes of birds and others appear in others. So basically using these functions and training the discriminant, the classification and the generation of the sentences, we have things like this. So we present this image to the network. It identifies the bird as a grosbeak, and then it says it generates this sentence because it has a red head and a breast with a gray wing and a white wing and so on. So this is a kind of explanation of why this should be classified as that each particular bird. So Kentucky warbler because it has it's a yellow bird with a black cheek patch and so forth. So this is not exactly an explanation of what the convolution network is doing, because the convolution network is here on the side, but the whole system is learning to classify the images and to generate a description of the bird and why it belongs to that classification. So this is an example of how we can use these kinds of architectures to go way beyond what we can generally do with traditional classic machine learning. So other things are, for example, generating video. This is an NVIDIA demonstration that you can find online. The network was trained using actual video driving through the city, but then the network generates images in the video. This is a bit like a dream, because if you go back, it doesn't really represent a city, but the images follow each other naturally and it looks like you're driving through a city. Or you can use networks to generate images of people, of faces, or for example, for fashion, you can generate fashion models and things like that. So now a big question is whether or not we are already at this stage of we know that the techniques work and they are really useful and now we are taking advantage of them, or if we are still in this in this part of the hype cycle as it happened before, where we have lots of expectations that then become frustrated because things don't really work out as we were expecting. I am a bit optimist. I think we are already here because there are lots of real interesting applications where deep learning is working. But there's always, remember this danger. 50, 60 years ago, 70 years ago, people always also thought that the perceptron would learn how to read and write and speak and things like that, and it was really very far from that. So there is this danger that maybe we have too many expectations of this technology, but it seems that things are working out very solidly, and the results are each passing year they are more clear. So one thing that you can do during this week is to play a bit with the TensorFlow playground if you want. This is not actually a tool for anything, for any practical work, but you can go to this site and build your own networks and see how they perform with different data sets, and you can just try different numbers of layers, different numbers of neurons, activation functions, and see how the network is working and how it's representing the data in each layer here. So basically a way to play around a bit and see these concepts that we covered in this lecture. For next week, we will not have tutorials today. We still don't have enough subject matter to start practicing, but we'll start the tutorials next week. And by then, I would advise you to already have the system set up so that you can do the exercises. So one thing to do is to use AutoEncoder, which is what we used in machine learning. It's the same framework. You can just install TensorFlow 2 using the Conda installer. So Conda install TensorFlow GPU, this dash GPU, you can do if you want to use hardware accelerations. If you have an NVIDIA card, note that you need the NVIDIA drivers and CUDA and things like that. So they only work with these kinds of chipsets. Or if you don't want to use GPU, you just install the CPU version. For the kind of problems that we're going to solve, it's probably not going to make much of a difference because we're not going to do anything very complex, at least in this first half of the semester. And this is only for performance. It makes no difference on the actual results. Alternatively, you may want to use Google Colab. So if you don't have everything set up before next week, you just need to log into your Gmail account and then go to the Google Research Collaboratory here, and you have a Jupyter notebook that you can import TensorFlow into that and use it for the exercises. The only tricky thing that you need to do is to use this code in order to map your Google Drive into Colab. So you'll need to authorize the access of Colab to that folder of your Google Drive. But then after you do this, you can change directory to a folder in your Google Drive, and then you can use the data sets and save files and so on. So use Python and TensorFlow as if you were using it on your computer, only everything is stored on the Google Drive. But I would recommend having a local installation, so installing things on your computer. That will probably be more practical because this has some restrictions. You can lose the connection, or you have a few hours that you can use per day and things like that, so it may not be ideal. So to sum up, what we saw is artificial neural networks, backpropagation. This was a revision of something we covered in machine learning last semester, but the focus here is on understanding how deep neural networks work and how they can help you handle unstructured data. And the motivation for this is that when you're dealing with big data, unstructured data, there's a huge amount of unstructured information. So you can really work with that if you manage to extract some useful knowledge from that. And deep neural networks are great for that kind of problem. So the reason why deep neural networks started taking off so recently is mostly a combination of the amount of data available, the kind of algorithms that we have. Some of these tricks like rectified linear units, optimizers and things like that are relatively recent, and also the hardware requirements for training these large neural networks. So for this you can, I'll recommend reading this paper on deep learning on Nature. It gives you a good overview of the field, and also these chapters of the books for this part. Okay, so now I'll just change the hardware and log into the Zoom session, and we can discuss a bit for those of you who have questions. Okay, see you soon.